This video presents the use of carbon-13 NMR for the determination of molecular structure and contrasts carbon-13 NMR to proton NMR. So if you haven't already watched the videos on NMR theory and proton NMR, you should probably watch those before you continue with this one. So the first thing I'll do is present our first carbon-13 NMR, and this is an NMR spectrum of 1-pentanol, pentyl alcohol. And the first thing you'll notice about a carbon-13 spectrum compared to a proton spectrum is there's a much broader range of chemical shifts. We still use TMS as a standard, and that we still set 0 Hertz, TMS to 0 Hertz or 0 parts per million. And I forgot to label that our x-axis is still in delta or parts per million. And so we are observing carbons here instead of protons, and I've color-coded those, so the carbon that's farthest away from the electronegative oxygen resonates farthest upfield as we would expect. And so chemical shift in carbon-13 depends on the same factors that determine chemical shift in proton NMR, that is, that electronegative substituents de-shield carbons. Remember, electrons shield atoms, nuclei, from the magnetic field, so anything that pulls electrons away from the observed nuclei will shift their resonances farther downfield. So the carbon that's farthest away from the electronegative oxygen is farthest upfield in the spectrum. And as we get progressively closer to that electronegative oxygen, the resonances get farther and farther downfield, and the one that's obviously farthest downfield is the carbon that's actually bonded to that electronegative oxygen. It resonates at almost 60 parts per million. So as we see in this example, carbon-13 is useful for determining the number of different types of carbon in a compound. And once again, the place where the carbons resonate gives you an idea of their chemical environments. So the chemical shift gives us structural information just as it did in proton NMR. So in a closer comparison of carbon-13 with proton NMR, we've already mentioned that we have a broader region of chemical shifts, as we see in this example. A second difference between proton and carbon-13 NMR is that carbon-13 unfortunately is much less sensitive than proton NMR for a couple of reasons. First of all, carbon-13 is only 1.1% of naturally occurring carbon. Recall that protons are the major isotope of hydrogen. Carbon-13, on the other hand, is a minor isotope of carbon. And so that's one reason why carbon-13 NMR is less sensitive than proton NMR. Another reason is that carbon nucleus itself is not as magnetic as a proton. So for those two reasons, carbon-13 NMR spectra typically take much longer to run than NMR sample, given the same concentration of sample in the NMR tube. Sometimes we set up carbons with many more scans, many more pulses of RF radiation than proton NMR to get a decent spectrum. Another very big difference between proton and C-13 NMR is that there's no spin-spin coupling observed between carbon-13 atoms, and this goes back to the fact that carbon-13 again is only 1.1% of naturally occurring carbon. So it's very unlikely that you get two carbon-13s bonded to each other, and if they're not bonded to each other, they don't split each other, they don't couple. You just don't see that very often. Not enough to observe coupling between carbon-13s. Now, carbon-13 does strongly couple, is strongly split by protons that are bonded to it. And actually can be a problem. It's a problem because the splitting is so strong that you get these strong broad splitting patterns, doublets and triplets and quartets and multiplets, that are so broad that they often overlap. To get around that problem, we use, instead of a spectrum where we observe the splitting, we turn the splitting off using a type of carbon-13 spectroscopy known as PDC, or proton decoupled carbon. That decouples the protons, as the name implies, from the carbon, so there's no splitting observed. And that's what we're seeing up here. These each are a singlet, even though these carbons are bonded to hydrogens that actually do split them. Or, by the way the NMR experiment is set up, we're turning off the splitting between the protons and the carbons. it's possible to turn that back on, and that type of spectrum is known as a GDC, or gated decoupled carbon. We're gating off the decoupling between the carbon and the hydrogens, and that allows the splitting to be observed. And so what do we see when we do that? I didn't draw an example of that, but I did give you a table of the sort of splitting that we observe. And so, as you might expect, if there's no hydrogens bonded to an observed carbon, as in this case, so we've got 4 alkyl groups bonded to this sp3 hybridized carbon, there's no CH splitting, and you see a singlet. If you have 1 hydrogen bonded to a carbon, you see a doublet. If you have 2 hydrogens bonded to an observed carbon, you see a triplet, and 3, you see a quartet. So it's similar to the n+1 rule in proton NMR, except now we're observing splitting between a proton that's directly bonded to the observed carbon, and there's always one more resonance in our splitting pattern than the number of protons bonded to that carbon. So one more example below. So I've drawn a spectrum here that gives you the regions for where the chemical shift regions where some of the most common functional groups will shift observed carbon atoms. And so these regions right here are for alkyl groups. So if you've got a methyl groups tend to resonate if they're bonded to carbons in this region from probably about 5 up to about 20 parts per million. Remember, alkyl substituents in NMR are somewhat electron withdrawing, and so they're somewhat de-shielding, and so a methylene group will resonate downfield of a methyl group, and a methine will resonate on average downfield of a methylene group. We see that here. X up here is a halogen. Halogens can tend to have a pretty broad range, as we saw in proton NMR, of electronegativity values from about 2 all the way out to 4 for fluorine, 2 being iodine. And so there's a pretty broad range here of chemical shifts for the halogens, because there's a range of electronegativities, and that gives you a range of de-shielding around that carbon. Oxygen on average is more electronegative than most of the halogens except for fluorine, so it tends to resonate a little bit farther downfield, carbons bonded to oxygens. Nitrogens are a little bit less electronegative. Pi electrons, as we saw in proton NMR, tend to be even more strongly de-shielding. And so alkynes a little bit less so. Alkenes are out over 100. Aromatic protons on benzene rings, are in this broad range up from about 110 out to about 180 in my experience. Esters and carboxylic acids, that's the carbonyl carbon, are even farther downfield because they're not only de-shielded by the pi electrons, they're de-shielded by these electronegative oxygens. And esters and carboxylic acids, the carbonyl carbon in those generally resonates in the region of about 160 out to about 185. Ketones and aldehydes are really the farthest downfield. We're talking again about the carbonyl carbons, and those resonate between about 190 and about 210. Usually if they are saturated, that means the alkyl groups coming off of these things are saturated. They're above, they're lower field than 200, from about 200 to 210. If there's a double bond or a benzene ring that these pi electrons in the carbonyl are in resonance with, that moves the resonance a little bit upfield to a little bit higher, generally from about 195 to about 200, 190 to 200. So that gives you an idea. So again, the chemical shift that we see for carbon atoms gives us structural information, tells us the sorts of functional groups that the carbon is interacting with or is close to. And we see that in this last spectrum down below here of methyl acetate. So we'll begin with the red carbon here. That's just a simple CH3 bonded to a carbon, and it resonates right about where methyl groups resonate. We see that just up above here, just below 20 parts per million. Moving over to the green on the other side of the molecule, this green carbon is bonded to a very electronegative oxygen. We see that in the range where we would expect a carbon bonded oxygen resonates. This one's a little bit above 50 parts per million, 50 delta. And then finally our carbonyl carbon, this is an ester, and so that's in this region right here, right around, maybe 175, something like that, which is right in the region where we'd expect a carbonyl and an ester to resonate. One last thing that I'll mention that I found particularly useful, and that is the relationship between carbon-13 NMR spectra and the symmetry in a molecule. Very simply, fewer resonances. If you see fewer resonances in the carbon-13, remember you get a distinct resonance for each carbon, each type of carbon I should say. So if you see fewer resonances than carbons in a formula, that indicates that there is symmetry in a molecule. So what I'd like you to do now is pause the video and just predict the number of resonances that you would see for each of these molecules. And now I'll go ahead and do that for you. So in this molecule, we have 4 methyl groups that are all chemically equivalent, bonded to one central carbon, and so you're going to see 2 resonances. In cyclohexane, there's only one type of carbon, so there's only one resonance. You see a single resonance for cyclohexane. Disubstituted benzenes can often be distinguished if you have the same substituent coming off by carbon-13 NMR. And so this is a paradisubstituted benzene, and we have 2 different types of carbon here because these 2 carbons, the carbons that the X groups are bonded to, are identical, and the carbons that are ortho to those X groups are also identical. There's a symmetry plane right down the center of that benzene ring right there. So these 4 carbons are all identical, and these 2 carbons that are attached to the substituents they're different than the 4, but they're identical to each other. That's 2 different types of resonances. So we see 2 resonances here for the carbons. Here we have 1, 2, 3, and 4, and numbering around this way, you have identical carbons. So again, the carbons that the X groups are bonded to are identical. So we have 1 carbon here. I should label these maybe. So we got 1, 2, 3, and 4. So we have 4 resonances. Let me go back and label these others. So we have 1 and 2. So all of the 2s are identical, as are the 1s. 1 and 2. All the 1s are identical, and these are all 1s. Finally, 1, 2, and 3. So if you have a disubstituted benzene ring where both substituents are the same, you can determine the substitution pattern based on the number of aromatic resonances. Another useful way of using carbon-13 NMR. So with that, hopefully you are ready to begin using carbon-13 and spectroscopy problems. If you have any questions, as always, please let me know.